All right, for the second half of this chapter, we're going to be talking about series. So today is really just about identifying what a series is and learning about sigma notation and just being able to go back and forth between the sigma notation and expanded form. So just starting out with the basics. So let's read the definition here. It says, when the terms of a sequence are added together, the resulting expression is called a series. So it's as easy as that. The first half of the chapter, we would talk about something that looks like this first example here, a sequence where it's just a list of numbers. Series would be the same idea, would be that list of numbers, but each term would be added in the sequence. So there's an abbreviated form using the Greek letter sigma that's called sigma notation. So we're going to be moving back and forth between that sigma notation and what would be expanded form. So like this first example here was an expanded form. Okay, so example 1. So we're going to write the series in expanded form because it's given to us in sigma notation. So let me kind of break this down piece by piece about what each part of the notation means. Sigma itself, that Greek letter here, means sum, which is why this is a series. We're going to be adding up terms. This n here is called the index. Similar to the first half of this chapter, it just refers to what number term we're on. And then this number here, I should switch colors, is called the lower bound. It's where we're going to be starting point. And this number up here is the upper bound. It's going to be our ending point. Upper bound. So that's where we're going to stop. Okay, and then here is going to be the formula given that's going to help us generate the terms of the series. Okay, so here's what this is asking us to do. It's asking us to use the formula starting with plugging in 4 for our n and ending with plugging in 10. So I'm really going to show all my work just for this first example so you guys see what's happening. So the first time I'm going to start with my lower bound, which is 4, and then plug that in for n, and I'll get 10. And then counting by 1 with whole numbers, we're going to plug in 5 for my n, and then 6, and then 7, and then 8, and then 9, and ending with our upper bound of 10. So that's just me kind of doing some shorthand here, starting with, scratch work, starting with the lower bound, ending with the upper bound, and getting each term of the series. But now I need to write it in expanded form, which tells us we take each term of the series, which we just found here, and add each one. So to write my final answer, I'll write it down here. It's going to be 10 plus 13 plus 16 plus 19 plus 22 plus 25 plus 28. That is our expanded form of that series. Okay, let's try another one. Sigma notation. Here they use the variable k instead of n, but it has the same meaning. Our lower bound is 1 and our upper bound is 4. So that's what we're going to plug in for k. So for our first term, we're going to have negative 1 times, to raise to the 1 plus 1, which is 1. Then we'll plug in k is 2. So that'll be negative 2 to the 2 plus 1. That's negative 8. Then we'll plug in k is 3. So that's negative 3 to the 3 plus 1, so 81. And then k is 4, and that's our upper bound, so that's where we're going to stop. Then just to write this in expanded form, we would have 1 plus negative 8 plus 81 plus negative 1,024. Now you don't need to write the, plus minus. You can simplify that. So you can write it as 1 minus 8 plus 81 minus 1,024. And that's our expanded form. Okay, so going the other direction takes a little bit more work. So we're going to write each series in sigma notation. So I need a few things. I know I'm going to be summing. I'm going to need to decide what my upper bound and lower bound are, and I'm definitely going to need a formula. So let's start with that idea of finding the formula. So what you're going to do is think of this just like it's a sequence, like we did in the first half of the chapter. So think of, we have 10, 15, 20, up to 250. So we ask ourselves, is this arithmetic, is it geometric, or neither? In this case, we have an arithmetic sequence. We can see that there's a common difference of 5. Between each term, we're adding 5. So my D is 5. So let's come up with a formula for that. For arithmetic, we know it's Tn equals T1 plus n minus 1 times D. So let's use some of the information that we have to find a formula for Tn. So we know that T1 is 10 and D is 5. So we have Tn equals 10 plus n minus 1 times 5. Now if I distribute and combine like terms, that's Tn equals 5n plus 5. So that's our formula here. That'll give us any nth term of the sequence. Okay, so now we say I need to figure out what my lower bound and upper bound are going to be. So put a number here and here. So I ask myself, well, what would I need to start with? What number would I need to plug in for n to get this first 10? Well, we know 5 plus 5 is 10, so our n should just be 1. So that's our starting point. That's fairly easy. But now the question is, what does our n need to be in order to get 250? So you might want to do a little bit of scratch work with that. You're trying to find out if I want my term to equal 250, what would n have to be? So you could subtract that 5 and then divide by 5 on both sides, and you'll get that n is 49. So that's our upper bound. And there it is. After all that work, now we have our full sigma notation, upper bound, lower bound, and our formula. Okay, same idea with this one. We're trying to write this in sigma notation, so the first thing we want to get is our formula. So for getting our formula, just think of this series as a sequence. So it's 1 over 5 cubed, 1 over the 5 to the 4, 1 over 5 to the 5th, all the way up to 1 over 5 to the 15th. So I ask myself, is this arithmetic, geometric, or neither? In this case, I can tell it's geometric because in each term, I'm just multiplying by 1 more, r to the r equals 1/5. So then coming up with that formula, we know it's Tn equals T1 r to the n minus 1, and we'll plug in that T1, which is 1 over 5 to the 3rd, and the r that we know. So it's Tn equals 1 over 5 cubed times 1/5 to the n minus 1. And then that's our formula. So I'm going to write that here. 1 over 5 to the 3rd times 1/5 to the n minus 1. Now the question is, what's our upper bound and what's our lower bound? Now the lower bound is always pretty easy because if I plug in 1 here, 1 minus 1 is 0. Anything to the 0 is just 1, so I just get back my first term. So we're starting with n equals 1. That's not tricky. What takes a little bit more work is thinking about what the upper bound is going to be, because you need the last term to equal 1 over 5 to the 15th. So we want 1 over 5 to the 15th equal to the formula that we just came up with, and then we need to solve for that n. So let's see, one thing I could do is multiply by 5 cubed on both sides just to get rid of this. So that'll become 1 over 5 to the 12 equals 1/5 to the n minus 1. Notice here we can get like bases and then set our exponents equal. So this is like from chapter 10. We can rewrite this as 5 to the negative 12. Inside parentheses, this is 5 to the negative 1. And now we can see that these exponents can be set equal because they have like bases. So we get negative 12 equals negative n plus 1. And then we get that n is 13 once we rearrange that. And then that's our upper bound, 13. And so there we go. We have our full answer in sigma notation. I'll box that so it's clear. Okay, that was just a few of the basic examples. There's more problems to try on Schoology. Again, that's homework assignment 11-4.